Hello guys, welcome back to my channel. We're now going to be looking at the integration of tan to the nx, and we're looking at the reduction formula aspect of it. Now, while most reduction formulas, technically speaking, are based on integration by parts, sometimes certain manipulation might just lead to something else. Taking for instance in equal to, we can rewrite the function as tan x times tan to the n minus 1. The problem with that is that we know how to indeed integrate tan x, but that's going to lead to a function known as ln, which we don't want because we want a pattern in terms of tan. So I know that if I write it in terms of tan squared is connected to sec squared, and if you integrate any aspect of sec squared, it's going to go back to tan x. So you have to use a certain level of reasoning to rewrite the function to integrate. So I'm first going to start by saying in is equal to the integral of tan to the n minus 2x tan squared x. So using up the laws and indices here. But we know that 1 plus tan squared x is equivalent to sec squared x, which would imply that tan squared x is equivalent to sec squared x minus 1. So this is the identity we're applying right here. Let me just put this in a box. So technically speaking, this is going to become in equal the integral of tan to the n minus 2x in bracket sec squared x minus 1 dx. Never leave that out, right? That's going to be very important there. Let me just condense this. Good. Now once again, just similar to how we did cos, we get to this point where we realize that we have a bracket, we have a product. We can't split a product, but we can split a sum or a difference. So I'm going to be expanding this integral. So I'm going to have in equal the integral, two brackets here, of this times this, which is going to give me tan to the n minus 2x sec squared x minus tan to the n minus 2x dx. Now we can split it. So I'm going to have in equal, because when we integrate a sum or a difference, we can split the integral, equal the integral of tan to the n minus 2x sec squared x dx minus the integral of tan to the n minus 2x dx. Now, in becomes, if we look at this part keenly, we realize that we have the integral by recognition here. Let me just quickly remind you what that says. It says if we have, let me just fix this up neatly here. If we have the integral of f of x to the n times f prime of x dx, then this is just f of x to the n plus 1 over n plus 1 plus c. That is by recognition. Let me condense it so we can get some more space. So does this apply to this? Yes, it does apply. The differential of tan x is sec squared x. The power is n minus 2. So based on recognition, it says all I need to do is to add 1 to the power of the function divided by the new power. So I'm going to have in equal tan. Now n minus 2 plus 1 would be n minus 1 x over n minus 1 minus. Now look at this integral. When we compare this to the original function, the power here is simply 2 less than what the original function is. So that can simply be written as in minus 2. And there goes my recognition formula, not my recognition formula, my reduction formula for tan x. And this is tan to any integral power. Now please bear in mind that n represents any power of, and tan must be a natural number, you can know. Alright? And n of course would have to be greater than or equal to 2, because bear in mind you have n minus 2 here, and you don't want to go into the negative realm. Now I could attach this condition here that says that n must be greater than or equal to 2. Alright, and that's it. Now that we have derived the reduction formula, we're going to apply it to a question. say we want to find the integral of tan to the 6x, which we can simply just call I6, because bear in mind that In was equal to the integral of tan to the nx dx. So that's comparison we're using. So here's what. If I were to take 6, and this is the part that you need to watch right here. If I put 6 here, I'm going to get 4. Put 4, I'm going to get 2. And put 2, I'm going to get 0. So it would be easy to start from 0 and build it up. So I'm going to just find I0. Now to find I0, we can simply use the original integral, which would be the integral of tan to the 0 x dx. And we have to use the original integral because this formula is applicable when n is greater than or equal to 2. Alright? Now, any function raised to the 0 is 1. So I'm going to have I0 equal the integral of 1 dx. So I0 technically is equal to x. Now that you have I0, we can find I2. Alright, putting 2 into the reduction formula to find I2, I would have I2 equal tan x, because if you put 2 minus 1 here, it's going to be 1 over 2 minus 1, which is also 1, minus In minus 2. 2 minus 2 is 0, so it's going to be minus I0. So I2 would be equal to tan x minus x. Bear in mind that we found I0 already. Now we can move up to I4. I4, going back to the reduction formula and replacing n by 4, would be tan cube x over 3 minus I2. But we have I2, so this implies that I4 is equal to tan cube x over 3 minus I2, which is tan x minus x. And you can break that down. I4 equal, and you could even write it as 1/3 tan cube x minus tan x. Alright, let me write this properly. Minus tan x plus x. Alright, reduce this to get some space now. Good. Now that we have I4, we want to move on to find I6, which is actually what the question had asked us to find. Let me see if I can adjust the space here. Now I6 would simply, going back to the reduction formula again, replacing n by 6, I would have tan to the 5 x over 5 minus I, and of course you replace n with 6, you have I4. Alright? I don't have to tell you exactly what is going to happen now. Since we found I4 already, we're going to replace all of that by I4. So I'm going to have I6 is equal to tan to the 5th x over 5, I'm going to write this 5 properly, minus all of that. So you have 1/3 tan cube x minus tan x plus x. Let me just remove this so we can have the space to write the final line. And then all we have to do is simplify. So I'm going to have I6 equal tan the 5th x over 5 minus 1/3 tan cube x plus tan x minus x. And now we can add the plus c, which is a constant of integration. Alright, so here we can see, we can also see a general pattern here, because if you notice, you'd have 1/5, 1/3, 1. So you realize that the denominators would have actually been the set of odd numbers, right? But that's a pattern that can also be investigated the next time as well. So that is my reduction formula when integrating to the 6. Now I want to use an add power and show you that we might have to make a few manipulations to do that.